Thanks for having me at this year's SIGTIP workshop, and the talk I'm going to present to you today is called a computational model for the assessment of mutual intelligibility among closely related languages. And essentially the idea behind this talk was born out of the notion that as a speaker of a given language, in my case German, I can often partially understand speakers of languages that are related to German, for example Dutch. So a sentence like this in German, mein Name ist Jessica, ich esse gerne Brot, trinke gerne Wasser und gehe gerne schwimmen, would have the Dutch version, mein Name ist Jessica, ik eet graag brood, drink graag water en ga graag zwemmen. Now the English translation for the sentence would be, my name is Jessica, I like to eat bread, I like to drink water, and I like to go swimming. And what we could see in this sentence as linguists, but also as maybe speakers of these languages, is that there are some similarities in the sentences, not only orthographical similarities, but also similarities in the sounds of the sentences. So this is the notion of mutual intelligibility, and it has been proven that this depends on several factors, and we can broadly distinguish between linguistic factors on the one hand and extra-linguistic factors on the other hand. Within the linguistic factors, we have things like a shared lexicon, orthography, similar morphological structures, phonological similarities, but also the modality the sentence was presented in, so spoken or written modality. Within the extra-linguistic factors, the most important one is the previous exposure towards the target language. And then there are things like the attitude towards the target language that play a role for mutual intelligibility. Now, when it comes to studies that have been done on mutual intelligibility, these studies are usually psycholinguistic experiments. And one of them is Goskens and Swarte 2017, and they presented a large-scale study on mutual intelligibility of Germanic languages. And they do so by using a spoken and written cloze test, essentially a text with gaps that need to be filled in by the speakers of a language. So the text comes in the target language, and the gaps, for these gaps there are some word lists, and then they have to fill in the words, and based on that we can decide how mutual intelligible the sentence are. In total, they tested 954 participants, which is quite impressive. That's why it's a large-scale study. And they tested 5 different languages, namely Dutch, German, English, Swedish, and Danish. But for the sake of this talk, we concentrate on the Dutch, German, and English results only. And we will directly have a look at that in this plot over here. So these are the results of the spoken cloze test by Goskens and Swarte 2017. I concentrate on the languages I just told you about. And what you have on the y-axis is the mutual intelligibility scores. And what we can see basically is that the language pair Dutch-English, so a native speaker of Dutch having a text in English, and German-English are the languages where we have the highest scores, and then the other language pairs follow. What you can also see in the plot is that you have some dark gray bars and some light gray bars, and the light gray bars is what they call inherent intelligibility. Basically, that is the intelligibility if we do not take the extra-linguistic factors into account. So if we have a participant that had no previous exposure to the target language at all. Now, obviously, this is something that might be a bit difficult to achieve, and that is the reason why we only have the light gray bars in the end of this plot, but not for the previous languages, Dutch, English, German, English, and Dutch, German, because they couldn't find participants that are Dutch speakers and have no exposure of English, for example. Now, previous language exposure is the strongest factor for mutual intelligibility scores, especially if we have a look at the previous data. Now, when focusing on the minimum of exposure, so the inherent intelligibility, then things like lexical distances, the amount of cognates, and the orthographic distances, measured usually in Levenshtein distance, are the most important factors for the scores that we saw previously. Now, what we want to present to you today in this study is a computer-assisted method to assess mutual intelligibility in Germanic languages, and more specifically, I will concentrate on Dutch, German, and English for that again. Now, what is the advantage of our approach as compared to the previous experiment I presented to you? We present a uniform method that can be adapted to various languages, but also we know that testing human participants is a time and resource consuming effort, especially if you have over 900 participants, right? So A second problem that we have with testing participants is that it's hard to find participants with no exposure to another language, because especially a language like English is a common lingua franca. So this might be problematic. Why is that problematic? Well, if we can get rid of all extra linguistic factors, what we would remain with is just the linguistic factors, and that might be something interesting. And if we want to test linguistic factors only, I propose that our computer-assisted method is a good starting point for that. Now, for testing mutual intelligibility computationally, we then need a model that is first able to model word comprehension, because this is essentially the process we are dealing with, and secondly, a model that has a cognitively valid approach, because we want to compare this model to the data of human participants. Now, the model we are opting for is Linear Discriminative Learning, and it is a model that was developed in the discriminative lexicon framework by Bayern and colleagues in Tübingen. It is essentially a model of language processing that is exploring the cognitive mapping mechanisms that are involved in language learning, and more importantly, it provides us with a method to model word comprehension, and this is exactly what we need. Now, in linear discriminative learning, the word comprehension route is conceived of as a mapping of phonological form onto meaning. And you can see that in this example here. On the left-hand side, we have the phonological form for dog, in this case presented as a diphone cues or digram cues. And on the right side, you have the semantic representation for a dog, things like animate, four legs, fur, floppy ears. And obviously, since this is the model, this gets translated into numerical values. And this is the word comprehension process. Now, from the mathematical point of perspective, this is implemented as multivariate regression, and we are using the phonological form matrix C then to map it onto the semantic matrix S. Now, what the model does during training is it learns to relate the phonological cues to the semantic matrix, and it establishes some association weights. And these in turn we can use to predict a semantic vector during testing that is then used for measuring the comprehension accuracy, so to understand how well a word form is actually understood by the model. For this process, we then need phonological cues and also meaning representations. And with the phonological cues, we are opting for cognate sets that are derived from Kluge's dictionary. That is a total of 340 word forms in German, and obviously we added then the reflexes in Dutch and English to that. Also, because we are dealing with phonological forms, we wanted to have a phonetic transcription, and we added that, and also phonetic alignments using the edictor tool by Mattis List. And then we reduced the phonetic detail using Dolgopolsky sound classes. Why did we do that? Because first of all, the Dolgopolsky sound classes are used in historical language comparison. They are known for showing good results, but also what we wanted to achieve is an approximation to the process that participants do. So basically, if they are not linguistic expert, they might not know the differences between the sounds, but they might notice that a sound in one language that is labial might relate to a sound that is labial in the other language, and this is the process that we can achieve with the Dolgopolsky sound classes here. We are also playing around with two different representations, that is full forms on the one hand and trimmed forms on the other hand. And for the trimmed forms, we are using a trimming process by Frederick Blum and Mattis List that was proposed last year. Now, trimming means, in this sense, that we are getting rid of inflectional endings. So this is especially important if we are dealing with Dutch or German verb forms that have the en infinitive ending in the end. So we're getting rid of that to see how well the model performs if we just present the stem of the word forms. For the meaning representation then, we will go ahead and use the multilingual concept net number batch word embeddings, and the idea behind this is that we want to have word embeddings that represent all three languages and that are similar in meaning. Now, to check if the word embeddings are actually similar in meaning across the languages, we computed the cosine similarity values, and this you can see in the density plot over here. Now, on the x-axis we have the cosine similarity, and what we can see here is basically that the majority of data is located around 0.9, means that there is a high cosine similarity across the languages, with German Dutch having the highest cosine similarity values, and German English, Dutch English being a bit more spread out across this scale for cosine similarity. Now, the first step in our modeling process is then to evaluate the model on the cognate data of individual languages to see if the model can actually deal with all three languages in this study. Now, sadly, we had to get rid of one word form, and that is due to the fact that the number badge vectors didn't provide us a meaning representation for one form in Dutch, and that means obviously that we also deleted the English and the German reflexes of this word form, and we end up with 339 forms in total per language. We present these word forms from the languages in 4-gram, 3-gram, and 2-gram chunks of sound classes, and then we are experimenting with the full word forms versus the trimmed word forms. And these are the results. So on the left hand, the full forms, on the right hand, the trimmed forms. Color-coded are the gram chunks, with the dark gray bars on the right always representing the 2-gram chunks. What you can see here is that the 2-gram chunks provide us with the worst results in the comprehension accuracy, which is on the y-axis, and the other gram chunks, so 4-gram chunks and 3-gram chunks, provide us with excellent results for word comprehension accuracy, meaning that the model can deal with German, Dutch, and English data as long as we present the data in 4-gram or 3-gram chunks of sound classes. Now, let's go to the interesting part, and that is the evaluation on the cognate data across languages, so essentially the mutual intelligibility process, right? We're dealing with the same setup, 339 forms in total, the same size of chunks, and full forms versus trimmed forms. And first of all, we want to concentrate on the data for the full forms. And what you can see here again is the color coding for the chunk size, and on the y-axis you can see again the word comprehension accuracy results. Now, what you can see in this plot is again that the 2-gram chunks did not provide good results, and that is not surprising, seeing that on the individual languages we also had problems, right? The best results we get for the language pairs German English and Dutch English, and this is totally in line with what we saw with the participants' data from Gooskens and Zwarte 2017, which is very nice. Now let's have a look at the trimmed forms. The y-axis is still the same, and you can see that the bars are rising a bit, meaning that we get better results for the trimmed forms, and actually the picture changes a bit. So previously German English, Dutch English was the best results. Now the best results we are getting for German Dutch and Dutch German. Again, like in the previous plot, the language English as the native language provides us with the worst results. So if I'm going back to the previous plot, you can see for English the bars are slightly lower than all the other bars in this plot. Now, what does that mean for our model? Let's discuss this. We get the best results with 4-gram and 3-gram chunks, and better results for trimmed than for full word forms. For the full forms, we have the best results for Dutch English, which is totally in line with Gooskens and Zwarte's data. Now, for the trimmed forms, the best results we get for Dutch German. English is the least advantageous native language in our setting, but this is also the case in Gooskens and Zwarte 2017. So again, we can replicate the results of the human data with our computational model here. We find a higher accuracy for German English than for German Dutch for the full forms, but we find the opposite effect than if we are using trimmed forms. And then for Dutch English, we find better results than for Dutch German for the full forms, but again, the opposite effect for the trimmed version. Now, why is that the case? I told you that when we are trimming the word forms, we are getting rid of inflection endings, and that means we are dealing with stem forms only. And apparently in that sense, if a speaker knows how to ignore these endings, we get better comprehension results. So morphological knowledge, the fact that there are endings and that we can safely ignore them, affects the comprehension results in our study. Now, my takeaway message for you is that we present a computational model here to test mutual intelligibility across languages. We are doing so using linear discriminative learning, and this is successful. So it's a model that we can actually use to model word comprehension processes. Now, our data shows similarities to human comprehension results, and that is in turn for us means that it's making the model a useful tool to assess mutual intelligibility. Now, obviously, nothing comes without limitations. limitations, and I also briefly want to mention that we tested 3 Germanic languages only in this setting. Obviously, this needs to be extended to other languages and potentially even to other language families to have a broad picture over this computational model and its usefulness for mutual intelligibility. And also we tested on cognate data only, which gives us the high results that we have. We need to extend that to non-cognate data, maybe present random word lists, but this is something for future work, and I'm looking forward to doing that. And with that, I want to leave you with thank you, grazie, Hafna, danke, and dankjewel.